Hey, welcome ladies and gentlemen to your 8.3 note guide, and this is all about series. This is the last note guide of this chapter. It's kind of a short and sweet kind of chapter. Notice the objectives up here. It's talking about that you should be able to write a series using sigma notation. Sometimes people say sigma, sometimes people say summation. And I actually say both as well. So sigma versus summation, same thing, and we'll talk about that here soon. And then the other thing you're going to do is find the sums of finite arithmetic and geometric series. So in advanced algebra, we talk about the sums of finite series, where in pre-calculus we talk about infinite sums and of geometric series. But that is, again, a little bit of the difference between the classes. Anyway, so what is a series? And sometimes students really miss this point, so I really want to make sure that you're hearing me. A sequence, which is what we had just been talking about in section 8.1 with arithmetic and geometric sequences, and then in section 8.2 with recursive sequences. That is just an order or a list of numbers with a certain pattern. So just like this, where you put commas between them, and you can see that you're going up by 2 there. Now, series is different. Series is the sum of the terms of a sequence. So instead of listing 1, 3, 5, 7, you're going 1 plus 3 plus 5 plus 7, and actually giving a sum, which in this case would be the value 16 if this was your sequence. Notice it has to be finite to get a sum, but like I said, certain geometric series, you can come up with a sum as they converge, but again, we don't talk about that in this class. Anyway, so bottom line, folks, sequence is a list of numbers in a pattern with a pattern. Series is the sum of all of those values in the sequence. So a series can be finite, ending, or infinite, which goes on forever. And this is when we get into sigma notation. And you hopefully have seen this symbol before, but if not, that's okay. I'm going to pretend you haven't. Again, some people call it summation. Actually, I'm not sure now that I think about it. I think I use the word sigma more. But anyway, so it is, let me just say this. It looks very, very complicated, and I always know that when I first show this. So just kind of, again, bear with me. But all this is saying is that you are going to have a sum, which is why we tend to call this a summation, where we're going to start with the first term, the initial value, and go all the way up 6 terms. So notice over here we have 1, 2, 3, 4, 5, 6 terms in this sum or this series. So this is, again, because we're dealing with a sum of a sequence, we call this a series. The rule, or the explicit rule here, is 4 times n. So notice we have 4 times the first term, 4 times the second, 4 times the third, 4 times the 4, and so on. And when you, oops, let me try to squeeze this down. Oh, I can't seem to move it. Hold on a minute. Okay, there we go. So once we simplify it and actually find the sum, the end answer, if you want to call it that, is 84. So that is just kind of a very, very quick summary of sigmas or summations. And we now, let me just, again, because you've not seen it more than here 30 seconds, so let's show you an example on how we do it long-handed. And again, kind of like I've done this whole chapter, some of the stuff I say might be a little too slow or redundant for you. If that's the case, just proceed at your own pace. But I'm just kind of keeping in mind that some people have not seen this ever, and it's very, very straightforward as long as I take it kind of slow here. So what is this summation telling me? It means that I'm starting at 2, I'm ending at 5, and we're going to put the value 2, which is your first, or well, technically it's the second term, but anyway, it's going to be 2 squared minus 1. So I started with 2 being put in there, and then I'm going to add 3 squared minus 1. So notice what's changing here is the value I'm inputting in for I. That value is going to increase by 1 all the way up to 5. So I'm at 3, 4 squared minus 1 plus 5 squared minus 1. So notice I started with 2 because it's telling me that right here I'm starting at 2. Sometimes it starts at, a lot of times it starts at 1. But sometimes it does start at 0. In this case it started at 2. So 2 going up 1 each time, 3, 4 until you get to 5. You stop at 5 because this up here says that. And now literally all you do is simplify and add those values together. So let's simplify this a bit. 2 squared is 4, minus 1 is 3, so we have 3, so that's what this gives me, plus 3 squared is 9, minus 1 is 8, plus 15 plus 24. So I'm just simplifying each one of those terms, and then I'm going to add it all together, and that is my answer. So what this is the sum from 2 to 5, the second term up to the fifth term of this sequence, I squared minus 1, is going to be the value of 5, or 50. So let's kind of see if you have this down. Oops, as I'm kind of moving things around. There we go. Okay, so this one, notice the term value starts at 0, or the term number starts at 0 and goes to 4. So, and my explicit rule is 5 minus 2j. So this is the rule right here. So I'm going to go 5 minus 2. The very first value I put in for j starts at 0. And then I go to the next one. And keep in mind that this is where it does take, you know, I'm writing out every step here. And this is where some people might not feel they need to, and that's all good. Just make sure you know what you're doing here. So, and I shouldn't say that. You do need to show your steps in your note guide. I'm talking about in your practice. At that point, you obviously can not have to show every step, but especially a note guide that you have to reference here later on, you definitely want to show your steps. And I can't talk and write at the same time, so minus 2 times 2. So notice here's 0, here's 1. And actually, you know what I'm going to do? I'm going to highlight that. Notice there's my 0 term, first term, second term. Plus 5. There's my third term and my fourth term. So that is it. That's how far I have to go because of this value right up there. Is starts at 0, goes all the way up to 4. That's what we wanted. Now we're just going to simplify it. Just make sure you do your simple arithmetic correctly. So let's see, we end up with 5 plus 3 plus 1 plus -1 plus -3, and that bad boy gives me 5 for a sum. So the sum of the terms from 0 to 4 gives me the value of 5. Now, what is my expectation when you're doing this long-handed? You know, you don't have to show all that top work. I would just expect this right here so I can double check that you are getting the right values for each one of those terms, and you know what? Then you are set. So you don't need to show all that much work. But remember, the final answer really is in the cloud, which is just the number 5. Okay, so see, summation is kind of fun, pretty straightforward. Now, the interesting thing is we are taking summation or the sigma notation and writing it out, expanding it out and finding the sum. Can you do the reverse? So can you go from a series, because a series is just a sequence with addition signs between it. So can you do a series and write it into summation notation? Well, that's what we're going to try next. So here we go. It says, write a series using summation or sigma notation hint, is the series arithmetic, geometric, or neither? So that's the trick here. You need to know what type of series we're dealing with. So looking at this, I can see I'm adding 2 here, adding 2 here, adding 2 here, and blah. Now we're not talking about recursion here. We're talking about really explicit rules of arithmetic and geometric. So we're going all the way back to section 8.1 and making sure you're remembering that stuff, because that's what you're going to need here. So I'm going to write first that we're talking about an arithmetic sequence. I know the d value, the difference is 2, or I'm going to add 2 each time. And the other thing that you might want to note to yourself is that it's finite. Notice it has an end, unlike letter B, example letter B. Then here's the trick. Again, just like note guide 8.1, so nothing here is new. Find your rule, okay? Find the rule, just like what you've already been doing. So I know a sub n equals my initial value 5 plus 2 times n minus 1. So there's the explicit rule of an arithmetic. And then, of course, we simplify it, right? Doing some mental math here. And I will say that if you write it as 3 plus 2n or 2n plus 3, it's fine. And you'll notice I've been writing it the other way, 2n plus 3 in the first note guides from 8.1, because it mimics slope and y-intercept form, that, mx plus b. But really, I will say that I tend to, in the higher level maths, I tend to write it like this. AP Stats, you write it like that, or statistics, but also as you move up through the ranks in general. Anyway, but it doesn't matter if you write 3 plus 2n or 2n plus 3. But you do need to simplify it down to that. Now, you need to practice drawing your sigma, which is just like that. I bet you can do it just like that, right? Did you see what I did? Let me do it again, because I've had lots of practice. I start this, go horizontal, come down so that you're level, down this way, come back and up. So do it a couple times so you get good at it, okay? So here is my sigma. In this case, I always start with 1. Very rarely do I start with anything else, because we tend to think in terms of first term, second term, and third term. 6. Notice we have 1 term, 2, 3, 4, 5, 6 in this series. And again, it's a series, not a sequence, because it has pluses between them. You're talking about a sum. And then we just put in this rule right in front, or behind, not in front, behind the sigma. And that is it. So we start at the first term, end with the 6th. How do we know that? Because this is our first term right over here. That's our first term. Whoa, I don't know what I just did. Sorry, you guys. And then we have 6 terms. And this, oh, geez Louise, is the final answer. Okay, so a lot of what we've already been doing. So now let's try this letter B. I'm going to try getting over there. Make you all nauseous by moving the screen around so fast. Sorry about that. So again, decide if it's arithmetic or geometric, or neither. In this case, if I do a ratio 10 over negative 5, that would give me negative 2. If I go negative 20 divided by 10, that is negative 2. If I go 40 divided by negative 2, it is negative 2. So we've got a geometric here. So I'm going to erase that now and write a couple notes to myself. So I know it's geometric. I'm going to just go geo. I know my common ratio is negative 2 from what we've done in the past. And as a reminder, notice it has dot, dot, dot. This is an infinite series. I almost said sequence by accident. Let me get the explicit formulas. So a sub n equals negative 5, which is the initial amount, times your ratio, or again your growth factor, decay factor, if you want to think of it that way, and to the n minus 1. So this is those formulas that we used, or that explicit rule formula that we use in section 8.1. That again, I give you the rule, but you need to know what it means and how to use it. And now that we have that, we just have to write it with the sigma. So here's my sigma. I'm going to start at 1, go up to, ooh, we can't count this, right? Here's the first term, second, third, fourth, 1/5, and then it goes all the way to infinity. So because it doesn't end, we put infinity right there, and then we put our explicit rule right behind the sigma. And that is pretty much it. So not a lot of challenge here. A lot of, just taking previous information, as long as you understood that, obviously, and just extending on it. So there, it's something that looks very, very complicated. And definitely if you know someone that doesn't know that information and you kind of show it, people get very impressed with that whole sigma notation stuff. It's very exciting stuff. Okay, so a couple formulas again that I actually give you. We give them in advanced algebra, but not in pre-calculus. So this is kind of your first intro to it, and then we hit them a little harder in pre-calc and expect them to know them by heart. So this is the formula for finding a sum of a finite arithmetic, this right here. And S stands for sum of whatever term you're referring to equals the number of that term times the quantity, the first term plus the last term divided by 2. Okay? And if you really look at this, not to get too, theoretical, because this is really not that big of a deal, but if you look at where you take the sum of the first term and whatever term you're talking about divided by 2, folks, that is an average. That's like if you have 2 tests, you're adding them together, dividing by 2 to find your average score. So just kind of keep in mind that math formulas are good, they are, but sometimes they hide the basics of what they're doing, kind of like tax forms. So anyway, sum of finite arithmetic series. That's the formula. We'll be using it here in a moment. The sum of a finite geometric series is given right down here. Notice you would need to know your initial amount. You would need to know your R value. And you need to know your term value that you're interested in. So those are, this is not anything that is too complicated, but I will say this. Notice that you need to know your R value for the geometric series, but you don't need to know your D value for your sum of your arithmetic formula. You'll see how that works here in just a moment. So actually I'm going to leave those formulas right there for us. It says determine, in example number 3, determine whether the series is arithmetic, geometric, and then find its sum. So letter A is in summation or sigma notation. Looking at it, I would hope if you're looking at this explicit formula right here, you can say if it's arithmetic or geometric instantly, just like this right here. So looking at this letter A, without a doubt, you should know instantly that that's a geometric, because that just looks like that y equals ab to the x, or again, everything that we've been dealing with up to this point. The initial value, or the a sub 1, is going to be equal to 4, because this right here is that initial amount. My growth factor, or again my R value, is 3. So we know all sorts of information there just by looking at the formula and or the summation notation. So this is where you kind of have to, like I said, having a formula is fine, but you need to really know what you're looking at. Notice that we are starting with the first term here, and I'll highlight this. We're starting with k equals 1. Now we chose to use k instead of n, not a big deal. And we're going up to the 16th term. So let's kind of fill in or use this formula that I have up here. So I'm going to say that we're going, I'll just leave it like that. Okay. The sum of the 16th term, of the first 16th term, so you have all these terms, 16 in a row that you're adding up together, will equal the first term's value, which is 4. So I'm using this formula right here, times 1 minus the ratio, which is 3, to the nth, or the final, which is 16. Like, how many terms do you want? Over just 1 minus 3. So this, and if it helped to say n equals 16 to remind yourself, because you are dealing with 16 terms here, do that. So notice we put again that common ratio, or the initial amount, and then 1 minus the common ratio raised to the 16th term over 1 minus 3. Sometimes the biggest obstacle with this formula is just being able to put in the calculator right for order of operations. So we have 4 times, in the parenthesis here, I'm just going to write out what you'll get just so that you can make sure that you're doing that in the calculator right. So it's 2 million. Ooh, I think, hold on, let me just write it down here, 215. Maybe I have my, I wrote it down really fast. And I think, looking at it, I have my commas in the wrong spot. 215, 23, 360. So what do we have there? We have hundreds, thousands. So we have 21,523,360 times 4. So your final sum for the first 16 terms, so if you listed all 16 terms, added them up in your calculator, you would have gotten 86,093,440. That is a lot of a savings with the formula. So the formula is saving you a ton of time by not having to list everything out and then calculate the sum. Okay, so that is how you use the finite geometric series. Again, note that the things you need would be the initial, the first term value, the common ratio, and then of course knowing what position or how many, in this case 16 terms that you're going to be adding together. Okay, letter B. Same kind of thing, but now notice that this is not an arithmetic, or excuse me, a geometric. This is an arithmetic. If it helps to list out a series of, part of the series, by all means. So you could put in 1, put in 2, put in 3, put in 4 to get kind of part of the series down. Notice we wouldn't want to list all 22 of them. That would take a long time. So I'm going to erase that just to get that out of the way. Just looking at it, remember I've said that this looks a lot like slope-intercept form of an equation because it really is. So just a reminder that this is arithmetic. My common difference, or my slope, is 11. I know I'm dealing with 22 terms here that I definitely do not want to list out because that would be a pain. But we do definitely need to know, if you look up here, you need to know that first term and the last term of whatever it is of the series that you're dealing with. So to do that, I am putting in 1 into that explicit formula. So I'm going to go -9 plus 11 times 1. So I need to get my initial value. So I'm putting 1 in for j because it's the first term. Simplifying it, that gives me 2. And then the last term would be the 22nd term. So I get -9 plus 11 times 22. And that, when you simplify it, will equal 233. So at this point, oops, I keep trying to spread it out to make it a little bit easier for myself to, and I keep writing all over everything. Actually, you know what I'm going to do? I'm going to erase this, because what's happening is I am going to run out of space because I'm writing awfully big. 233. Okay. So looking at that sum formula to the left, up at the top left-hand side, so we have the sum of the first 22 terms. So if we had all 22 listed, we could just throw them in our calculator, but it's going to be a pain in the rear end to do, equals, notice that it says n, so that's going to be 22 times the initial amount, here's the initial amount, 2, plus the last term, which is this right there, 233, divided by 2. Remember I was talking about that's the average, so it's the first term plus the last term divided by 2. So you're finding the middle, and then you're multiplying it by how many terms you have, which is 22. It's an awesome formula. It actually is an awesome proof that we do prove in pre-calculus. But the sum for this series is 2,585. So if I added all 22 of those term values together, I'd end up with 2,585. Notice I am using the notation S sub 22 because that reminds me that we're talking about 22 terms that we're finding the sum of. Okay, so we have 2 more examples here. Let me kind of make this one nice and spacious so that we can kind of see what's going on. Okay, so we have to decide arithmetic or geometric. So looking at it very quickly, I can see it's arithmetic. Why? Because we're adding 4, adding 4, adding 4. So it's arithmetic. This is again in my notes. D is equal to 4. My a sub 1 I have, which is 2. My a sub what though? Equals 58. I don't know how many terms there are, because this is the first term, second term, third, fourth, and all sorts of other ones, but we don't know what term that is. That is a problem, because I need to know what that is, because that is what we put into our formula. See, we need to go S sub n. We need to put that value right there in there. So we don't have a big piece of the puzzle. So no fret, don't worry about it, because here's what we do. We know that that's our end value equals, we know our initial value is 2 plus n minus 1 times common difference of 4. So let me just say what I did there. I need to find that, and I need to know what term number that is. So I'm putting it in the explicit formula for the arithmetic, and I am going to just solve for n. So I know that I want the n1 is 58. I know the beginning term value is 2. I know our difference is 4. So let's find n, and that would be the number of terms to get to 58. Now, could you do this long-handed? Yeah, probably. You can add 4, add 4, add 4, add 4, add 4, add 4 until you get to 58 and don't lose count. And do it that way. I will say this, that again, with most assessments, they make you do it algebraically. So, it would end up being like 3,536, so that you don't tend to do that. So, so let's solve this. Yes, so we have 58 equals 2 plus 4n minus 4. What do we have there? Negative 2, we're adding that. So we end up with 60 equals 4n, and n is equal to 15. Okay, so yeah, it wouldn't have been so bad to trial and error to that. But like I said, that that's not going to be what an assessment is. The assessment's going to make you have to figure it out long-handed. So when kids sit at an assessment for 2 hours with these kind of problems, that's when we know we just need to pull it away, because they're not understanding really how to use the algebra to find the term values. So just kind of keep in mind that this is definitely one of those I shouldn't say time tests, but it's pretty it's pretty obvious when students know what they're doing with it. So I now can say that this 58 is the 15th term, because we solved it right there. So a sub 1 is the first term, which is 2. A sub 15 is the last term value, 58. And now we just need to plug and chug it right into the formula. So we have S, instead of n, we put 15 equals 15 times, remember this is where you're just doing the average, the first term plus the last term divided by 2. And when you calculate that, and again, make sure you're careful with those calculators, do order of operations right, you should end up with a sum of 450. Yay. Okay, so that's an awesome problem. I'd almost put a C, or like a star by C, because that is one that comes up in assessments. Not horrible to do, but you can see how you might forget how to do it because of finding that term number. Just kind of practice that, make sure you're all good with that. Letter D, a regional soccer tournament has 64 teams. In the first round, there's 32 games are played in each round. The number of teams decreased by 1/2. That's talking geometric, right? You're dividing by half, or dividing by 2, or multiplying by 1/2, however you want to think about it. It says, write a rule for the number of games played in the 9th round, and then, which is really, write a rule is find the explicit rule for the geometric, like you did in section 8.1, and then find the total number of games played in the tournament. So let's kind of say what we know here. We know it's a geometric. We know the common ratio, not n, r is equal to 1/2. And we need to know, again, how many terms, so this one, again, we can do like I did and showed you in letter C. This is the one I'm going to say, you know what, if you take 32, because it's such a small value, 32 divided by 2, you're at 16. Divided by 2, you're at 8. Divided by 2, you're at 4. Divided by 2, you're at 2. And then you're at 1. If you add those, you're talking about 6 rounds. So this is an example of sometimes, common sense is just going to play out over the algebra. And algebra is never meant to make it more complicated. It's actually, algebra is all about shortcuts, really, to reasoning. So just this one, I'm going to just say 6 rounds. Make it easier on us. So a sub n equals, the initial amount of games is 32. Our rate is 1/2. So this is the initial amount times the growth factor, in this case decay, n minus 1. So this right here is the first thing they're asking. So it says, write a rule. There's the rule. So that's what they wanted, the explicit geometric rule. Now they're saying find the sum. Now again, if you're talking about 6 rounds, you could literally, seriously, go 32 plus 16 plus 8 plus, all the way to that 1. But I'm just, or actually, yeah, the 1. But with that said, I do want to make sure you see how to use the formula. So the sum of the 6 terms in this series is equal to, and you know what? I said 36. How many times do I make mistakes, you guys? I apologize. There we go. That probably would make more sense to y'all. I'm sure you're all like, no, not 36, 32. Okay, anyway, so 32 times 1 minus the growth decay rate, which is, actually it's the ratio. I should keep using that though. 1 minus the ratio raised to the 6th term. I'm going to do that. Divided by 1 minus 1/2. And I'd probably, in the calculator, substitute 0.5 in for 1/2, obviously. You should end up with 32. And again, just to make sure you're doing the calculator right, let me just write, I could give it to you as a fraction, but let's not, shall we? So there's your value inside that parenthesis. Make sure you're doing that right in the calculator. And you know what? You'll find that the total number of games played in the tournament is 63 games. And any of you guys who are in athletics, this is something you guys do all the time. So again, if you went 32 plus 16 plus 8 plus 4 plus 2 plus 1, you know what? You get 63 games. So I'm not taking away common sense. I'm just saying if it were a much larger numbers, you definitely want this shortcut. So it doesn't seem like a shortcut right now for this example, but it is a shortcut with very large numbers that you can't necessarily calculate very quickly longhand. Okay, so that is a nutshell of summation or sigma notation. So you kind of get used to finding sums of series. Again, there's a huge difference between sequences and series. Sequence is what we've been doing with commas between. Series is the sum, or you're adding your sequence together, your values of your sequence. And then just making sure that you're kind of getting used to being able to find the sum using those formulas. Again, that asterisk that you put in example C, make sure that you know that is a noteworthy problem. That's kind of like that $1 million question on an assessment. So if you have any questions on this, of course, I am going to be here to help you in class to answer those. Take care. Thanks.